In today's video, we're going to look at gravitational force on the planetary scale and Kepler's laws. So we know that there is a force between all objects with mass, and it turns out that we can actually quantify that force. So the force of gravity between two objects with mass is equal to the gravitational constant times the first mass times the second mass divided by the distance between the masses squared. When a couple of notes here, the gravitational constant is given here as 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. This value is given on the AP equation sheet. So that's good to know. The next thing I'd like to point out is that the distance between the masses, this R value, is distance. Be careful, it doesn't exactly mean radius. I'll make a sketch here of two planet-sized objects. The distance that we're going to measure is always from the center of gravities of the objects. So there's our representation of R. It doesn't go to the surface, it goes to the center. Let's try some examples to see if we can use this formula. Find the gravitational force between a 500-gram mass and a 100-gram mass placed 1 meter apart. Well, this is a pretty straightforward plug-and-chug problem. So the first mass is 500 grams, which corresponds to 0.5 kilograms. The second mass is 100 grams, which corresponds to 0.1 kilograms. And the distance between them is 1 meter. I must assume that this 1 meter is the distance between the centers as I drew up above. But we're just practicing using the equation in this situation. So I'll write the equation like I always do before I solve a problem, and then I'll plug in the relevant numbers. G was 6.673 times 10 to the negative 11th. Oops. M1 was 0.5, M2 was 0.1, and then I'm going to divide that by 1 squared. So then I'll get out my trusty calculator. And I get 3.3 times 10 to the negative 12th. Now this is not a very big force, and when I look at these objects, these are pretty small objects. You can think about the 500-gram mass that we have in the classroom that kind of looks like a cylinder, and the 100-gram mass that is a bit shorter. They're not going to have a huge attractive force. There is an attractive force between them, but it's not very large. In fact, it's, what is this? 1 trillionth or 3 trillionths of a Newton. Let's try something with larger numbers. Practice problem 2 says, find the gravitational force between the Earth, here's the mass of the Earth, let's check that out, and an average human. I put average in quotes because who knows. But we will use the equation to solve this. So the masses, the first mass is the mass of the Earth. That's 5.98 times 10 to the 24th kilograms. The mass of the human is 70. And the distance, the radius of the Earth, is 6.37 times 10 to the 6th. Ooh, and this is in meters. So what we are assuming here, I'll just draw a quick sketch of the Earth. Here's the Earth. Big blue marble. There's North America, South America, Africa, Europe, Asia. Okay, I'm getting too into it. So the person is standing on the surface of the Earth. This is not to scale, right? but their distance to the center of the Earth is essentially the same as the radius of the Earth. We are not taking into account their height because compared to the radius of the Earth, that is just a tiny, tiny amount. Okay, so now I can proceed with the formula. So I've got Fg equals the gravitational constant, m1, m2 over r squared. 6.673 times 10 to the negative 11th times 5.98 times 10 to the 24th times 70 all over, these numbers are huge, 6.37 times 10 to the 6th, and that radius in the denominator is squared. So now I will go to my trusty calculator and solve that. 6.673 EE negative 11th times 5.98, EE 24 times 70 divided by 6.37 EE squared. EE to the 6th squared. So I get a value of 688 newtons. Now, check this out. The person has a mass of 70 kilograms. If we take 70 times 9.81, we get 687 newtons. So the answer that we get by using the actual mass of the Earth and the actual radius of the Earth is the same as if we use 9.81. What this means is that if I take this formula and think of m1 as the mass of the Earth, that means that this part of the formula must be equal to g, because essentially what I have is that the force of gravity, the gravitational force on some mass on the Earth, is equal to that mass times g, or 9.81. So that's pretty cool. Okay, let's try this one. What happens to the gravitational force on an object when its distance from the center of the Earth is doubled? Okay, so gravitational force, we're leaving G, M1 and M2 the same, and we're asking what happens when we double R. So what's going to happen is we're going to divide that value by 4. So the force is divided by, by 4. Okay, so again, this formula, this gravitational force formula, gives us the gravitational force between any two masses, M1 and M2, that are separated by a distance. It's the distance between their centers. And then we also have this gravitational force constant that we need. What this gravitational force constant does, by the way, is it makes the units work out. It makes the masses divided by the distance squared come out to the correct newtons. Okay, so now we're going to look at, so gravitational force, the reason we're studying it right now is that it is a cause of centripetal force. Gravitational force can be one of the things that causes things to move in a circular path or an elliptical path. And so what we're going to look at here are the consequences of that. And I'll just read a little paragraph here to get us oriented. In the early 1600s, Johannes Kepler proposed 3 laws of planetary motion. Kepler was able to summarize the carefully collected data of his mentor, Tycho Brahe, with 3 statements that describe the motion of the planets in a sun-centered solar system. By the way, this was a little controversial at the time. There were still lots of people that thought that everything revolved around the Earth. Kepler's efforts to explain the underlying reasons for such motions are no longer accepted. Nonetheless, the actual laws themselves are still considered an accurate description of the motion of any planet and any satellite. Kepler's 3 laws of planetary motion can be described as follows. Okay, the first law is that the path of the planets around the sun is elliptical in shape, and we studied ellipses in class. The center of the sun is located at one focus. So basically, this is what this would look like. I'll draw a roughly elliptical path, and I'll draw the sun. I'll draw the sun, and then I'll just draw a dot. So this is a focus of the ellipse, and this other dot is a focus of the ellipse. Then we would have a planet orbiting the sun, and it would follow in this elliptical path. Please note there is nothing located at this other focus. There's nothing there. Okay. Number 2. An imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal intervals of time. So they're talking about this line here. So as the planet travels, what we're going to be looking at are these areas that are swept out as the planet travels around the sun. So I think this is best viewed in an animation. So I'm going to click over to one of the animations that's available on Canvas. Oh, it wants me to have let me try this again. Here we go. Okay, so here is an animation with the sun and a planet. We can see the planet going around, and then the red area, and then the black area, and then the red area. These are all equal areas. The size of those areas is the same. And we can see that the consequence of the equal areas rule is that the planet goes faster when it's closer to the sun, and the planet slows down as it gets farther from the sun. So a consequence, planet moves faster when it's close to the sun and slower when it's farther away. And when we think about that, it should make some sense. When the planet is closer to the sun, the force of gravity is bigger than when the planet is farther away from the sun. And if the force of gravity is bigger, and the force of gravity is the centripetal force in this case, then what happens is that the radius got smaller and the velocity got bigger, and the FG got bigger as well. And on the other end, over here, the FG got smaller because it's farther away, and the speed decreased and the radius increased. We're going to take a look at another animation, and this is also available on Canvas. It's a Phet animation. This, well, I'll just press play on this just to start. This is kind of a cool little animation where you can see the Earth going around the sun, and down in the corner it tells us how many days have passed. I can turn on the gravitational force, I can turn on the velocity of our planet, and I can trace the path. That's pretty cool. Now, you can modify our orbit here. So I'm going to press play, and I'm actually going to move the Earth. Oh, I feel so powerful. I'm going to move the Earth a little bit and press play again. And now what's going to happen is I'm going to get more of, it went out of frame. I'm going to get more of an elliptical path. It'll come back around. There we are. So in this picture, now we can see more of an elliptical orbit, and we can see how the force gets bigger as the Earth gets closer and less as the Earth gets farther away. This is an exaggerated ellipse. Our ellipse looks more like the original one, which really looks a lot like a circle. It is not very eccentric. Okay, the third law that Kepler came up with is that the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. So here's what that means. Here's the sun. Here's Earth. Here's Earth's orbit. Here's Mars. Here's Mars's orbit. Oh, make that a little bigger. Come on, Mars. There we go. Okay, so here's Mars, Earth. So Earth and Mars have different distances from the sun. So I'll call this R sub E for the orbital radius of the Earth, and I'll call this R sub M for the orbital radius of Mars. It turns out that the Earth and Mars have different year lengths. So the Earth's period is what we call a year. That's what we care about. We live on the Earth. And the symbol I would write is a symbol for period, and then I would put a little sub E to indicate I'm talking about the Earth. And Mars is going to have a different year. It's going to take a different amount of time to go around the sun, and I'm going to call that tau sub M. So Kepler says the ratio of the squares of the periods of any two planets. So if I say the period of Earth squared over the period of Mars squared is equal to the ratio of the cubes of their average distances from the sun. So that's the distance from the Earth to the sun cubed over the distance from Mars to the sun cubed. Sometimes you'll see it written like I've written it there, and sometimes you'll see people use the means extremes property to swap two of the values. So you could write it as the period of the Earth squared over the orbital radius of the Earth cubed equals the period of Mars squared over the orbital radius of Mars cubed. Okay, so Kepler's third law is sometimes referred to as the law of harmonies. It compares the orbital period and the radius of the orbit of a planet to those of other planets. So here we're comparing the Earth to Mars. Unlike Kepler's first and second laws that describe the motion characteristics of a single planet, the third law makes a comparison between different planets. The comparison being made is the ratio, well, it says the same thing again, is the ratio of the squares of the periods to the cubes of their average distances to the sun is the same for every one of the planets. And so here's an example. If you actually calculate out, if you take Earth and Mars and their period, that's a year, and their average distance to the sun, and put it into this formula, you indeed get the same ratio, or very, very close to the same ratio, and that's the same for all of the planets in our solar system. All right, that concludes the notes on Kepler's laws, and I look forward to working on worksheet 4 with you.